Okay, what we're going to do in this set of notes is kind of expand on this connection between the definite integrals and area. Now, if you'll recall from our prior lectures that the area under the curve, the region that's bounded by the given function and some vertical lines along like your left and right bounds and your x-axis. We can also do it to the y-axis, which we have not talked about yet, so we're going to do that in this set of notes. And we also have not talked about area between curves, but we started our discussion of creating the Riemann sums as an area problem. And so what we're going to do is we're going to go back and remind ourselves, how can I use definite integrals in order to find the area under a curve? All right, so we're taking a look at just kind of a review of what we had done before, that when we were finding this area between the function and the x-axis, provided that the function was always non-negative, then the definite integral is going to be the area under the curve. And we're doing our bounds from a to b, and we use our definite integral notation. Now, and then just as a reminder, what we just learned in our notes earlier from section 5.4 would basically be to calculate this using the fundamental theorem of calculus would be to find the antiderivative of the function that you have here in the integrand, and you would simply calculate the net change f of b minus f of a, because remember, definite integral is the net change, and since it's the net change, because the function is always positive, it does happen to also equal the area in this case. Alright, so what we would basically do in this problem is that we would sketch the area so that we can see and visualize what we're looking at. We make sure we know what our boundaries are from a to b, the left and the right bounds. We basically set up our definite integral, and then we perform the integration. Now, when we perform the integration, if you're on the calculator section, you're going to use your function int each time you want to do this. If you are on the non-calculator section, you're going to use your fundamental theorem of calculus, the fact that the definite integral can be found by looking for the net change in the original function. All right, so for example, we're going to come down here to example 1, and we have a curve. And what we have here is they didn't actually give us your bounds, but what they're giving you is the fact that the function and the x-axis, they kind of are bounded together, and we're looking for this area. So you pretty much are going to be able to find the bounds yourself by finding the x-intercepts. And then so here's our work from Algebra 2. Set your function equal to 0, factor, use your zero product property, so we get 0 and 4. So the boundaries on this example are going to be going from 0 to 4. And then we basically calculate our area. Our area is going to be the bounds from 0 to 4 of our function dx. So it's very straightforward. So we can use the calculator to verify that you're going to get 32/3 here. I'm going to show you using the fundamental theorem of calculus just to show you that it works, because we can do the antiderivative of 4x minus x squared. So the antiderivative of 4x, using our nice little power rule, we add 1 to the power, and then we would divide the 4 by the power, so that would give us a 2. Minus, I add 1 to my power, and then divide by 3. And then remember that this is one of our antiderivatives, but we're doing a definite integral, so we want to make sure we're showing that we're going to then evaluate this net change from 0 to 4. So we put in our bounds, and then we go ahead and we calculate this net change by plugging in the 4 and calculating that. 2 times 4 squared minus 1/3 times 4 cubed, and then subtracting, because you're doing net change, plugging in the 0, which of course is simply going to be 0 in this case. And you can verify to yourself that the answer is going to be 32/3. And then you can also verify this using function int on your calculator, that you get the decimal approximation of 32/3. So that area in the first quadrant that was under the curve that was an upside down parabola is going to be the 32/3 square units. All right, now let's take a look at this example. We want to find the area bounded by the parabola x squared minus 4, y equal to 0, and x equal to 4. So now let's think about y equal to 0. What are we talking about when we say y equal to 0? This is the x-axis. So we've shaded it in here. I had the x-axis. X equal to 4, well, that's essentially telling you a vertical line, right? So that's giving me this bound that we're looking at. And then the parabola is giving me the third part of this bound. Oops, sorry, I can't sketch very well here. So I'm looking for this little gray shaded region. But that's nothing more than the area between the function and the x-axis. Now, the point that I don't know right now is the a. So I have to do a little bit more work in order to calculate what the lower bound is going to be. So I find my x-intercept, or the intersection of the two curves, the parabola and the horizontal line on the x-axis. So we, again, factor and we solve. We get plus or minus 2. But remember, you've sketched it and you know that we're basically going for the 2. So our lower bound is going to be 2. Our upper bound is going to be 4. So when we go to do our integral, our area, again, because it's always above here, is going to be the integral from 2 to 4 of our x squared minus 4 dx. Again, I'm going to let you use function int to verify with the calculator. And again, coincidentally, we got 32/3 again, but let's verify that with the fundamental theorem of calculus. That using the fundamental theorem, I would take the antiderivative of x squared, x cubed 1/3, minus 4x. So I get the simplest antiderivative, and we're evaluating net change. So I'm going the net change between 2 and 4. So I have those bounds in there to show that I'm doing a definite integral in the net change. And that when I calculate this area, then we're going to get plug in our 4 to get the upper part. So 1/3, 4 cubed minus 4 times 4. And then we subtract what we would have gotten on that function when we plug in 2, so 1/3, 2 cubed minus 4 times 2, and again you can verify using arithmetic that you're going to get the 32/3. Alright, now let's take a look at the next scenario, and this is the new part of this that we're going to be talking about. That what if I talk about the area under the curve, except instead of saying I want the area between the curve and the x-axis, I really want between the curve and the y-axis. And so we're going to have to make some changes to our idea of area. Now again, when we are taking a look at this and we're doing area, when we did it with the x-axis, we wanted to make sure that the curve was always above the x-axis on the positive side. We are going to want to make sure that when we're doing this, that we want the curve to be always on the right side of the y-axis this time, because you want to make sure that all of the values that we're going to use are going to be positive. But now notice also that I'm making some changes here. That when I am looking at this one and I want to have between the function and the y-axis, I have to change my perspective. That when I am looking at this figure, I don't want to go as draw my rectangles vertically like I would if I was going the area to the x-axis. I want to draw my rectangles horizontally. And when I draw my rectangles horizontally, now the width of my rectangle is going to be a delta y, not a delta x. When I draw them vertically, the width is going to be a delta x. So we have to change this so that we get this in terms of y. And then the other thing that we have to change is that over here, you're going to have y, the height of the rectangle, as a function of x. But when we're over here, we need to actually find the x for the height. And so x is the height, and so we have to have that as a function of y. So we're going to have to do a kind of change in perspective. So up here, notice that instead of delta x, we now have delta y, or dy. Our width is now y, and then our height is now the x, so we have to have our function where we find x as a function of y. And then the third thing is to recognize that these bounds, that these are y value bounds. This is your low y value to your upper y value, because that's how we're running. We're running through the rectangles vertically now instead of horizontally, and we have a change in y, and y runs from the low to the high. So that's what you want to remember, that if it's dy here, that these are y values on your bounds. So you're basically going to do the same thing that we did. You're going to sketch your area, you're going to determine your boundaries, and remember that these are y values. You're going to set up your definite integral. You're going to make sure that you're using dy, because the width of your representative rectangle is going to be dy, and then you're going to integrate. All right, so let's take a look at this curve that we had. And, so there's going to be two ways to calculate this area that we're looking at. Okay. Now, a couple of things to notice here, and this is kind of why I don't necessarily want to do this to the x-axis, is because notice the x-axis is down here, and that's not part of the curve. So here's my x-axis. Now we will have a method of doing this by drawing the vertical rectangles in, but once we notice that we basically have a parabola that is bounded by the y-axis, we start to think, I think it might be better to do this problem by doing Riemann sums of rectangles that are horizontal. So I know that I'm going to have a delta y here, and that this height, when I find it, it has to be a function of y. I have to plug in the y to get the height, the x that I am looking for. So I make these changes before I start. Now on this, the y equal to 4, that's your horizontal line right here, y equal to 4. So we pretty much know the upper bound is going to be 4. Now the lower bound, we need to know the intersection of when our function has a y-intercept. So we're going to need to let x equal 0. Now, let's see, I probably have the work down here. I think they didn't really show you the work, but if I were to let x equal 0, then my y would equal 0 squared plus 2, which is 2. So that's fairly straightforward to find the bounds. Now the second thing that I need to do is I have to make some changes to my function. I need to have my x as a function of y. So what we're working with here, we need to take our y equal to x squared plus 2 and recognize that the height of our rectangle is now x. So I have to solve this for x. So it's going to become x squared equals y minus 2. So x equals plus or minus the square root of y minus 2. But now remember, why do I have two of these? Because one is going to be this side, y equals the positive square root, so you very quickly get mixed up between your x's and your y's. X equals the square root of y minus 2. This side is, again, I'm stuck on the y, x equal to the negative of the square root of y minus 2. So you actually have two pieces to this, because it's not really a function. X is not a function of y because there are two parts. But we only need between this portion of the curve and the axis. So this is going to be the g of y that we're going to use in our integral. Okay. And I believe I have this on the next page. All right, so here's our work again. We solved for x. We ignore the negative because it doesn't matter. And notice we're now going from a y of 2 to a y of 4. The x is our height. That's our function of y. And then my dy is my width. Now again, I can calculate this using the fundamental theorem. And again, you can verify it on the calculator using function int. Let's go ahead and show the fundamental theorem of calculus. This antiderivative, let's think about what we have here. I'm going to rewrite this as y minus 2 to the 1/2. And we're just going to play around with it right now because we really haven't learned a lot of shortcut rules about working backwards from this. But I think this one is easy enough that I can figure out what the derivative would be. So let's kind of start undoing the power rule part of it. So if I were to take the antiderivative, I would probably add 1 to this power. So y minus 2 to the 3/2. Now I would also think about the fact that if I go to take the derivative of this, I would not get this because I would have a constant in front of 3/2. So I'm going to do the same thing. I'm going to divide the power out. Dividing by 3/2 is multiplying by 2/3. And then I'm waffling a little bit here because there's really a chain rule problem here. If I were to take the derivative of what I have, would I get this? The answer is yes, because the derivative of y minus 2 is 1. So I'm kind of assuming that this must have been a chain rule problem where this is your derivative of the x with respect to y when I take the derivative when I have x equal to 2/3 y minus 2 to the 3/2. Technically plus c. So if you think about this, your derivative would be 3/2 times 2/3, 1, y minus 2, subtract 1 from here to the 1/2, times the derivative of y minus 2, which happens to be 1, and so that kind of works out. So we can reason out our derivative on this nice simple one. And we're doing a definite integral, net change, so we show that we're doing the net change from 2 to 4. And notice it made sense that these were y values because you're plugging them in for y. So we calculate our function value at 4, 2/3, 4 minus 2 to the 3/2. And then we calculate our function value at 2, 2/3, 2 minus 2 to the 3/2, which is going to be 0. And you can verify that this is going to give us 4 times the square root of 2 over 3. It's nothing but arithmetic. You have 2 cubed, which is 8, the square root of 8, which is 2 square roots of 2, which gives me 4 square roots of 2 over 3, right? So we're good with that one. So that's showing you the example of where we are basically going to the y-axis instead of the x-axis. Now we're going to look at example 4, another one here. So we have our curve, the arctangent. Okay. We have our line, y equals pi over 4, and y equals pi over 4 is this line right here. And then we have x equal to 0, which is the y-axis. So as soon as I see that I have that y-axis involved in this, notice the x-axis is not part of the region at all. I go, this is probably going to make more sense to do your rectangles horizontally. So immediately I know that I'm doing this area, and notice that I know that the definite integral and area are the same because the function, the area that I'm looking for, I'm using the function that is to the right of the y-axis. So I know I'm going to have everything in terms of y. So now let's think about what we need. I'm going to need to find these bounds. So I'm going to need this c and I'm going to need this d. But we pretty much already know d is pi over 4. We might want to think about our knowledge of our arctangent of x. When we plug in 0 for x, what do I get for my y value? The angle whose tangent is 0 is 0. So we know that c is going to be equal to 0, so that I get my bounds. I'm going to run my y's from 0 to pi over 4. And now I've got to switch my function around, because now the width of my rectangle is going to be dy, change in y, and my height is going to be the x, and I've got to find x as a function of y. So what we know, if y equals arctan of x, how do I undo an inverse function? Then your x has to equal the tangent of y. So I simply rearrange that. And so hopefully you can see down here that we're basically calculating the integral from our low of 0 up to our high of pi over 4 for our y values. There's the width of my rectangle is dy, and then the height of the rectangle, x, as a function of y by doing tangent of y. Okay, now on this one, I am going to wave my hands a little bit about finding this antiderivative. As of yet, because we haven't done our shortcut rules, we do not know how to find the antiderivative of a tangent. And so I'm going to wave my hands a little bit here. The answer does happen to be 1/2 natural log of 2, but we'll learn that part in another section. What I wanted to concentrate on now is just the setup of calculating this area. So for this problem, we are only going to verify with our calculator. So I will leave it to you to type this into your calculator and get your decimal approximation. Type this integral into your calculator using your function int, and then you should be fine and verify that that's going to be the answer. And again, this is mostly because a lot of this you'll see we'll do more practice with these areas. We'll come back to them after we have learned all the shortcut rules and be able to work through these. So that's like coming attractions. The rest of chapter 5, once we get out of this section and we understand what the fundamental theorem is let's learn all the rules for working backwards, all the shortcut rules, and then we'll come back through and practice this skill of finding area where we have shortcut rules. But for right now, I'm just concentrating on how do you set up the definite integral? How do we set it up to the y-axis? And so a lot of your homework tonight has a lot to do with the setup. All right, and then this is the third option, and again, we're mostly previewing just to get the idea of what happens now if I want the area between two curves where I do not have an x-axis or a y-axis involved in the problem. I have two different curves that I'm trying to find the area between. Well, the idea is we're going to use essentially the same idea. Like in this example right here, your first decision that you're going to have to make is whether you're going to do vertical rectangles or horizontal rectangles. And what you're looking for here is when you have your two curves and your regions, like here we have y equals e to the x, which is this curve, and then we have our parabola x squared minus 1, which is this curve. And then we have two vertical lines, which is basically giving me the bounds here and here. Now, essentially, when you look at this, you kind of have to start training your brain to recognize that this problem would make more sense doing vertical rectangles than it would be doing horizontal rectangles. And that would mean that we're going to be doing delta x for the width, or dx, because we're going to be letting the number of rectangles go to infinity. And then we have to worry about, well, how are we going to find the height of the rectangle? And hopefully you'll see that you basically, and this is what you have to remember, is your height is always going to be the top function minus the bottom function. That's your key in all of these problems. And you just have to identify what's your top and what's your bottom. So in this problem, your top, and because we're doing this, this is going to be the top y minus the bottom y, because you're doing the y values because we had a vertical rectangle. So notice that up here in my formula, I have y2 minus y1, where you have your functions, y is a function of x. I'm basically doing top minus bottom. That's what I'm looking for, and this would be the situation that I would do for this problem. Okay? And so basically, kind of following through with this one, I'll come back to the horizontal ones in a second. So I identify the top curve, I identify the bottom curve, I identify that this makes way more sense to do this as vertical rectangles, where the width would be delta x. And so when I set up my integral, what I'm basically going to set up is that I'm going to do the integral from my bounds, which they gave me, -1 to 1. Those are those x values. If you come back and look here, your a is going to be -1, your b is going to be 1. These are the bounds that we're doing. Okay. And then we can basically say our -1 to 1, and then this is the top y value, y2, minus the bottom y value, y1. So that's essentially what I'm doing. Now notice that they kind of played around in the formula, and I wouldn't put this in unless I had to, but if I'm on a calculator section it doesn't matter. Notice they put some absolute value in here. If you are on the calculator section, would it really matter which one's top and bottom if you just made it a positive distance? You'd be fine. So if I was doing this on a calculator, I would put the absolute value in. If I'm doing it not on a calculator and I have to do it by hand, I always just identify the top and the bottom, and I do the big minus the small when I do the subtraction. So we get to here, and this is what we're going to integrate. And I think we can do this one. This is simple enough that we can actually use our fundamental theorem to integrate. Let's show the work for that. If I want to integrate e to the x is the derivative of what? E to the x. Then we have, now that you have to be very careful with our minus, I'm going to do minus and then put parentheses. And then I'll take the antiderivative of x squared, x cubed 1/3, minus the antiderivative of 1, so that would be x. And then remember that we are evaluating this as a net change because we're doing a definite integral, so we're doing -4 to 1. So we show that we know that we're doing the net change. And then we plug and chug. We basically go e to the -4 minus my 1/2 e to the, oops, I don't know why I'm putting an e in there, 1/2 -4 cubed, and then I'm going to go ahead and do plus -4. I went ahead and distributed that. So that's the value of the function at the first endpoint minus the value of the antiderivative at the second bound at 1. So that would be e to the first minus my 1/3 times 1 cubed. We'll put parentheses in here. And then my plus 1. And I will leave you to verify that if you do a little arithmetic, we will end up with this 3e squared plus 4e minus 3 over 3e. I would leave you to verify as long as we make a mistake. I don't have my glasses on right now, so I'm going to fix something I just did wrong. I obviously can't read. The low bound was -1, not -4. So make that change. So it's -1 as what I was plugging in here. So this is my f of -1 minus my f of 1. My antiderivative plugging in -1 minus plugging in 1, and then we get our net change that we're looking for. All right, now let's look at one that goes the other way and kind of talk about the other formula. When I'm looking at this one, and we have the following curves, we have x equals y squared minus 2, so we have a horizontal parabola coming in here, and then we have our x equals y, which is nothing more than a straight line. And you kind of have to look at this and realize that you don't want to do top minus bottom, because here's the parabola and the line, and then here, after I hit this point, it would be the parabola and the parabola. You have to kind of make sure that when you visualize this that you can get a top function and a bottom function, but in this case when we do a horizontal rectangle coming across here, we're doing the top, we mean right, because we are moving left to right now, and then the bottom we mean left. And so we are still going to calculate this, but we recognize that it makes more sense in this problem to run our rectangles horizontally, which means that our width is going to be the change in y, or dy, and our height is going to be the difference in the x's, difference in x values. So we know that we're going to take the right x value, we'll say x2, and we're going to subtract the lower, or the left x value, x1, in order to get the actual height of the rectangle. So when we set this up, okay, a couple of things we got to worry about. We're going to need our bounds. Okay, now our bounds, this is my C to, this is going to be my D. We're going to have to find these values. And you may be like, well, how do I do that? I have to find the intersection of these two curves. Now be careful when you do your intersection. We have x equals y squared minus 2, and we have x equal to y. Make sure that I'm basically doing a system and plugging in x equal to y in over here and solving for y. Why did I solve for y? Because I remember that when I have dy, the width is dy, my bounds are y values. So I solve and I get my two y values here and here. And so those are going to be my bounds. And then I determine which is going to be the top and which one is going to be the bottom. The right function is going to be the line, and the bottom function, or the left function, is going to be the parabola, and I make sure I have them in terms of x equals, because it's the x that is the height. So then we can set up our integral, and we can run our integral from the top, the right minus the left. So this is the right x minus the left x, here and here. And our bounds on the y go here, and then our dy. And again, I can use my net change to do this. I'm going to rewrite this with some simplifying as y minus y squared plus 2 dy, which is nothing more than a polynomial. So we can find the antiderivative very easily. We would have y squared 1/2 minus y cubed 1/3 plus 2y, and we're evaluating this antiderivative for net change from -4 to 2. Well, I really need glasses. Y'all are going to laugh at me because I keep thinking those -1s are -4s. So -1 to 2, and then I simply have to plug and chug. So I have 1/2 2 squared minus 1/3 2 cubed plus 2 times 2. That's the value of the antiderivative at 2. And then I'm calculating net change. So now I need the value of the antiderivative at -1. And so I'm basically going to have the 1/2 times 1 minus 1/3 times 1 plus 2. And so I fill that in. And you can verify that this is going to give us 9/2 for that problem. All right, so here's another example. And this is one that's kind of interesting when we start to get in. Notice that in the examples I had previously, that there was one function on the top, one function on the bottom, one function on the right, one function on the left. And so what we see here is that we have a switch, that they intersect, and it switches from one being on the top here, the line's on the top, now the parabola is on the top. And so hopefully what you can see is that sketching these regions are going to be very, very important. And that when we're taking a look at this, I am going to decide to do my rectangles in a vertical fashion, so I do make that decision. So I know that I'm going to be doing width is going to be delta x, and then my height is going to be the change in y, so it's going to be y2 minus y1, top minus bottom, okay? And what you have to be careful of here is that we're going to have to break this up. We're actually going to have to do this with two integrals at the intersection point. We're going to have to go abound from x equal to 0 to x equal to whatever this value is, and then end up at x equal to 5, which is this upper bound. So we're going to basically break this up into two problems. I find the middle intersection point. I set my two curves equal to each other. X squared equals x plus 5. Get 0 on one side, factor, solve using algebra. So we have these two intersection points. Now we got two because one's here and one's here. Identify which one you want, which would be the 3. So now we're going to set up our integral as the integral from 0 to 3. And then notice that what I did is I took the top all of a sudden I was like, did this have a problem in it? Because this should be 6. This should be 6. Okay, all of a sudden I was like, there's a mistake in this. But the line was x plus 6, so this would be x squared minus x minus 6, and this does work out because they just had a typo on that. So coming down here, notice that I did the line minus the parabola. That was my top minus bottom. And then it switches. I did the parabola minus the line because you need to do top minus bottom. So we've split this into two. So when you're doing this, and again, just to show you the actual work from fundamental theorem, for this one, I would take my antiderivative. And the nice thing is, just be careful with your negatives. You would have x squared 1/2 plus 6x minus x cubed 1/3. This one we would evaluate from 0 to 3 for our net change. Then we would take, and now we do the other one. We take the antiderivative of x squared is x cubed 1/3. Then we have, now I'm going to go ahead and distribute this and think of this as minus x. So the antiderivative would be minus 1/2 x squared. I'm going to distribute the negative here and think of this as minus 6. So the antiderivative would be minus 6x. And we're evaluating that one for a net change between 3 and 5. So I will leave you to verify by plugging in 3, plugging in 0, calculating your net change, plugging in 5, plugging in 3, calculating your net change. Then you'll see that we get this 157/6 that we were for this. So I'll leave you to verify that portion of it. Alright, so basically this idea is that I would like you to be able to work on the setup of these problems. Decide whether you are doing a problem where you're going to go the area under the curve to the x-axis, whether you are going to do the area under the curve to the y-axis, or whether you are doing the area between two curves. And if it's area between two curves, can we do that area as one definite integral, or do we need to do it as two? Okay, so I'm going to let you, I don't want you to actually do the actual integrals for these. For homework before you come to class next time, all I want you to do is I want you to sketch each region. So I want you to sketch the region. I want you to determine what case we're in. Are you finding area to the x-axis, so between curve and x-axis? Determine if you're going to do between the curve and the y-axis, or determine if you're going to be between two curves. And then I basically just want you to write an integral representing the area. Now, we'll leave the actually doing the area and finding the value for another day. I think if you can just get them set up, that would be great.